we see dealloying or selective bleaching, that means that the noble metal stays and in the alloy the active metal goes out in the solution in the form of ions. So, there are many variations. One particular variation is de-zinkification. So, let us discuss de-zinkification. De-zinkification means zinc goes out in the form of ions from brass and copper stays back. And in that case, if we see some of the characteristics of de-zinkification of brass, that time actually copper plus zinc alloy, and in that alloy zinc goes out and copper stays back. So, finally, we will see that the surface is enriched with copper and depleted with zinc, and the surface becomes porous in nature and the strength of the brass decreases. So, if we see that it is observed in the naked eye and the surface become red in color compared to the original yellow colored brass. Generally, the yellow colored brass is 70-30, 70-30 brass, where 70% weight percent of copper and 30 weight percent of zinc, that constitute the alloy brass. Now, this becomes red colored from yellow color due to de-zinkification, and this red color because the copper enrichment happens on the surface. Then there could be two types of de-zinkification. One is layer type or plug type. So, generally in case of pipeline made of brass handling potable water, there we see that the inside surface uniformly that gets de-zinkified, and the entire surface, inside surface, that means the entire inside surface becomes depleted with zinc and enriched with copper. This is layer type. And plug type, that could happen. For example, if this is the pipeline and some part is de-zinkified or de-zinkification happens in some portion and another portion, the rest of the portion does not happen, nothing, it is uniform, almost uniform corrosion, but that localized section that could get the situation, that is de-zinkification. This happens in case of boiler water pipeline, and that handling the outside is gas, hot gas, and inside is water, and that time the plug type de-zinkification happens. That means the localized. So, if we have de-zinkification, then the surface becomes enriched with copper. Now, whenever we have, let us say A and B, these two elements constitute a particular alloy, and if A is noble and B is active in comparison to these two metals, that time if you have enrichment of that alloy with element A, that times we generally see that the corrosion resistance of that particular alloy increases, if that alloy is enriched with A. That means, let us say I have started with 70-30, if I go to 80-20, this brass will have higher resistance, corrosion resistance compared to this brass. So, this has high resistance, high corrosion resistance compared to this. So, now during de-zinkification, the surface becomes, this is the surface, initially the surface 70-30, let us say 70-30 copper by brass. Now, after dezincification, the surface become enriched with copper and there the copper content goes up to 80%, let us say. Now, that time the surface nobility increases, but the point is the copper what is enriched here, that is not a solid copper, it is basically a porous mass, and that decreases its mechanical strength. So, though the corrosion resistance improves, but actually the because of this dezincification the brass is losing its strength. So, this is another characteristics. So, that is why if you want to see whether dezincification is or has already started or not, the best way to do is basically seeing the mechanical property or the tensile behavior of that material. Now, before dezincification the tensile behavior is something, but after dezincification you will see that the strength decreases. So, that is one indication that dezincification is happening. Even if you do not see this color change, still you can see that there is a lot of decrease in strength. So, this is another characteristics of dezincification. Now, and of course, if you see that if you have a less zinc in a particular brass, that brass would have higher strength towards dezincification compared to the brass which has higher zinc content. Now, let us say if the zinc content is such that beta phase forms in case of brass phase diagram, if you go, you will see that the beta phase forms at higher brass zinc content. And if you have a mixture, let us say you have a mixture where you have alpha phase and you have beta phase, then the dezincification starts in the beta phase, and of course, this beta and alpha that also constitutes a galvanic cell, and it starts from here and then it extends to this alpha phase. This is one observation that is made, that is generally common in case of brass with higher zinc content and if it has beta phase in the alpha matrix. Now, fourth characteristic is whenever you have conducive condition, let us say you have crevice formation, let us say a pipeline, and in that pipeline you have some dirt particle. Okay. So, then you have crevice formation, like this dirt formation, there is a crevice, there is a crevice. So, that crevice, whenever crevice forms, initially the corrosion starts with crevice, and once crevice happens, then the dezincification goes on. So, whenever you have some foreign deposits, that would help dezincification. So, that is not good that is not good with respect to this dezincification phenomena. Now, as I have mentioned, the metal structure, this is the structure effect, metal composition, those are very important issue for in case of dezincification. Now, let us get into the mechanism part, why the noble metal stays back and active metal goes out in the form of ions. If you check the mechanism, there are actually three school of thoughts. One school of thought says that if you have copper and zinc, zinc preferentially goes out and forms zinc plus ions and copper stays back. So, in a system like this, zinc is going out in the form of ions, and gradually the system is getting dezincification. Now, in this theory, the main problem is if we want to, then we see that the dezincification gradually grows in the depth direction, but that time the small pores that forms, through that pore you have to have solution supply, and that would be a little difficult. So, that the rate at which dezinkification happens and the rate at which zinc dissolution should occur, that always does not match. So, that time you have some confusion regarding this. Now, second mechanism, which is almost well accepted theory, it says that copper zinc and copper both go out and then forms copper ion and zinc ion. So, both dissolve, that means the brass dissolve. So, if you have a brass surface, let us say this entire section dissolves, Now, once in a solution you have zinc ion and copper ion, since copper has higher reduction potential. So, copper E0 of copper is greater than E0 of zinc, as well as if you want to see the reduction potential of copper ion to copper and zinc ion to zinc, if you compare that, then this will be the situation. That means, even if you do not consider the standard reduction potential in the solution, the reduction potential and the reduction potential of copper would be always greater than reduction potential of zinc. Now, that time, since it has a higher reduction potential, copper will redeposit back. So, actually in this case the reaction is copper minus 2E, it goes to copper plus plus. Now, in this case it would be copper plus 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 2E goes to copper. So, copper redeposits back. Now, when it redeposits back, that time you have the situation would be like this section goes out and now you have copper enriched zones. And gradually once we have copper enriched zone, that becomes noble site or cathodic site. So, cathodic reaction would happen preferentially on these sites, and rest of the systems you have the same mechanism. So, actually zinc goes out, copper goes out in the form of ions, and then copper redeposits back because of the higher reduction ability of copper ion to copper. So, this is the second mechanism. Or the third one, people say that both the thing will operate simultaneously. So, this happens at the same time, this can also happen. This is the third school of thoughts. So, there we have mainly two mechanisms, and third one says that there could be combination of these two. So, that means this is the mechanism of dezinkification. Now, same will operate in case of denickelification. That means, when in case of copper nickel alloy, if nickel goes out, that time it is called denickelification. That time it also would be the same mechanism, both go out in the form of ion in the solution, and then copper redeposits back. So, these are the mechanism. So, now the point is, if we would like to stop this dezinkification, what we can do? So, one way is, now if we come to the prevention mechanism, so generally we would like to go for an alloy or brass where we have less of zinc. That time the inherent strength towards dezinkification would be better. Now, second case, that means a better alloy. Better alloy means we have a less susceptible alloy, that means we have less of zinc. Second case is, as we have seen while talking about the different ways to protect for protection of metals or alloys against corrosion, we have seen that somehow if we can take care of the solution aggressiveness, that means let us say I remove oxygen content, I remove salt content. So, that way also we can have a protection against this dezincification. So, you can have by aggressiveness of the solution if you can decrease it. Now, third case, if we can have a system where we add tin. In case of brass 70-30 brass, if we can add tin, that time that means add tin let us say 1%, then the brass is called Admiralty brass. Admiralty metal, and this tin somehow protects the brass, the material, from dezincification. How it does? What happens? This tin, it basically this makes the system inherently protective against dezincification. Fourth one is you can add phosphorus, arsenic, Sb, that means antimony. These are acting as an inhibitor. Those can act as inhibitor and inhibiting elements. Inhibiting elements, what they do? They redeposit on the surface of the metal. See, dezincification is starting, but when we are seeing that this step is occurring, that means redeposition of copper. But instead of that, if these elements deposit back and form a thin surface layer, so actually you are cutting this particular step. So, dezincification could be reduced to a great extent. Now, these are basically the overall picture of dezincification. Now, there are many more examples. Let us explain one particular phenomena, that is called graphitization. So, graphitization is a particular phenomena that occurs in case of cast iron, and the cast iron, when the cast iron is grey cast iron. So, that time graphitization happen. Now, this graphitization generally in metallurgy, the graphitization means the breaking down of pearlite into carbide, into carbon and ferrite. So, if we see the graphitization, of grey cast iron, So, that case as I have said that graphitization in case of metallurgy, it means that pearlite breaks into ferrite plus carbon. This is called graphitization. But in case of corrosion, this is a different phenomena. This graphitization, this is from metallurgical aspects. But in case of corrosion, this means dealloying. In case of corrosion, this means dealloying. What happens? If you see the particular structure of grey cast iron, there we have ferrite matrix, then we have graphite flakes, these are graphite flakes, these are graphite flakes, Now, that case graphite acts as cathode and iron acts as anode. So, you have a galvanic couple between graphite and iron. So, if you expose this thing into a solution which is mildly corrosive, that time this iron goes out in the form of ions and leaving behind graphite. So, there is a selective dissolution of iron and the graphite flakes stays back. Now, these graphite flakes are basically like this. So, if this section goes out, that means the iron goes out, but the graphite flakes would form a network and try to get attached to the surface. So, there would be a slight change in the surface appearance, but there would not be much of change in the surface dimension. So, the main dimension will remain same, almost remain same, but the because the graphite flakes are forming a network and that network actually holding the residue. Okay. So, these residue which is the corrosion product. So, actually the dimension does not change, but what is happening, this residue would be a loose mass, okay, and that loose mass actually is giving detrimental effect to the mechanical property of that grey cast iron. So, this is the bad part of graphitization of grey cast iron in corrosion fundamentals, where it is basically happening because of dealloying. Now, this thing does not happen if the corrosive nature of the solution is very aggressive. So, that time the corrosion is so fast, this actually the network does not form, it goes out. So, actually that time you have almost uniform corrosion, and so you always remain that surface would become always having the base metal surface, and this part would go off in case of highly corrosive system, highly corrosive solution. Now, this happens with case of graphite grey cast iron because graphite flakes forms, but it cannot happen in case of nodular cast iron. So, this is the nodules, let us say these are the nodules of graphite. These are the nodules of graphite. Now, when we have this dezincification, these nodules are basically no longer would be able to form a network. So, the entire residue will fall off. So, that time the surface would not have the nature what would be possible in case of graphitization of grey cast iron because of the network formation of due to the graphite flakes. And in this case, since the nodules cannot hold the residue, so this will fall off and the system will decrease its dimension, but the actual surface would always, let us say this much graphitization dissolution have taken place. So, this surface would have the same strength level of the base metal. So, this is not a problem for nodular cast iron. So, this is about the graphitization of grey cast iron. This is an example of dealloying phenomena also. And dealloying phenomena, by applying this dealloying phenomena, we can also develop nanoporous template of silver or gold. Nanoporous gold or silver substrate we can develop by this dealloying phenomena. So, this is basically helpful. This actual process, though it is not good for brass material, but this is good for something else, and because of this dealloying, gold or silver, nanoporous gold or silver, that can be made. For example, if you have silver plus zinc alloy, and that alloy, if you allow it to dissolve zinc preferentially, then if you have a thin film of these alloy, then the zinc goes out and the system would become like this. So, it was basically made of silver then, and the silver network would form, and this silver network will create a porous material and porous template, and those pore dimension will be in the range of nanometer dimension. So, the nanoporous gold or silver template can be made by using this particular phenomena called dealloying. So, its corrosion phenomena is not always bad, it is good in this case. By applying this simple principle, we can have a very good nanoporous gold or silver template. So, this is about dezinkification, dealloying, graphitization of grey cast iron. So, now let us get into another form of corrosion. So, that is basically the erosion corrosion. So, this is another form of corrosion, this is erosion corrosion, and now erosion corrosion is due to the relative movement of solution over the metal or alloy surface. So, now if this metal surface, this is the metal or alloy surface, over that the solution is, this is metal surface, and the solution is moving, and that means there is a relative movement between the solution and the substrate or the metal. Now, due to this movement of solution, if there is acceleration of corrosion, if there is acceleration of corrosion rate or acceleration of corrosion, that time the phenomena, that process is basically due to erosion effect of the solution. Now, if there is reduction of corrosion rate or deceleration of corrosion, then that will not be termed as erosion corrosion because of the flow of the solution. Now, before that, before coming to the deceleration effect, we always should understand that this erosion corrosion would generally increase the corrosion rate because of the relative movement of the solution over the metal surface. And let us say when the corrosion is happening, that time there will always be a sort of directional nature of the corrosion attack. Now, gradually the surface layer would go off, and then you will have, since the solution is flowing like this. So, the nature of attack would be like this, that means we have a directional nature of corrosion attack on the metal surface, and gradually there would be acceleration of corrosion. Now, if this solution movement is very high, let us say the solution movement is very high, that time apart from this dissolution effect, there could be wear effect, because of the movement of the solution, and if the solution contains lot of dust particle or in the form of slurry, that would also give the wear effect on the surface if the movement solution velocity is very high. So, wear effect as well as the corrosion, and then even if the wear effect is not there, only because of this movement there would be acceleration of corrosion. Now, let us say in case of pitting, we have seen that pitting initially forms like this, there would be several pits like this, and in case, and that for pitting one necessary condition is stagnancy of the solution. Now, if, and we have seen that even the experimental evidence shows that if the solution velocity increases, the pitting rate also decreases. So, solution increases, pitting decreases. Now, that means because of increase in solution velocity, one particular type of corrosion phenomena which is very insidious or very dangerous with respect to the material property under reuse, that time because of the solution velocity, pitting resistance improves or the pitting decreases. That could not be termed as erosion corrosion, because here there is a deceleration, there is a decrease in corrosion rate. There is a decrease in corrosion rate. This will not be a phenomena, this will not be under erosion corrosion. This is not an example of erosion corrosion. So, that means we have to always see if there is any acceleration of corrosion. And now, this metal, how this could be possible? Metal will go into solution, metal goes into solution, metal minus 2E it goes to solution, and the solution dissolution rate increases because of the erosion effect. How? Let us say if we consider a particular material, soft material, let us say that is lead or copper. The soft material, because of those erosion effect, there could be localized deformation, and that deformation could increase the, could possibly form a local galvanic cell, because the deformed part and undeformed part, that could be having a galvanic coupling effect, and so the undeformed part would dissolve quickly. Or if there could be a possibility of a deformed part which becomes embrittled, and then that goes off because of the erosion effect or the movement effect. This is possible in case of, and this is basically a dissolution of metal ion. Now, this can also be possible if there is surface layer. Now, let us say in this case we have a surface layer, this is the metal surface, this is metal, and this is passive layer, and let us say this is some oxide. Now, because of this erosion effect, now there could be a localized removal of passive layer. Now, once there is a localized removal of the passive layer, that means the metal surface is exposed to the solution, and then before the passive, another passive layer forms, by that time there could be little more dissolution like this. Now, second phenomena would be this part, there could be little more chipping away of this passive layer. So, again the metal surface is exposed to the solution or the corrosive, little more corrosion again happens, and there would be a formation of passive layer. So, before it forms another passive layer, till that period the metal surface is exposed to the corrosive, and that time the metal dissolution would enhance, and once the passive layer forms, then metal corrosion would be sluggish. But the point is, during that process some other part of the passive layer would get damaged again. So, during that process also the metal surface is exposed to the solution, dissolution happens, the rapid rate of dissolution happens before it repassivates. So, this is another mechanism by which erosion corrosion can happen. And where it could happen severely? For example, if we have let us say a pipeline, the solution is moving, and generally until unless the pipeline has a break or bent, let us say this is a bent, in the pipeline, till that moment the solution always achieve a linear flow, lamellar flow, and that is not that dangerous. But once the solution is changing its path, movement direction, that point, this place there could be a huge turbulence, and this turbulence effect is very dangerous if you consider erosion corrosion, and due to this turbulence this part of the metal bend would be susceptible to erosion corrosion to a great extent, and there could be a break in this section wherever turbulence develops. So, that means we have, whenever we have change in direction, that is a very susceptible part in the structure. So, we have the appearance, there could be appearance of whenever we have grooves, whenever we have gullies, whenever we have waves. So, that means this is wavy nature. So, that means the appearance of the erosion corrosion, those are rounded hole, so these are the appearance of erosion corrosion, and this can happen whenever we have a direction change or whenever we have a lot of residue or lot of dust particle is there in the solution. So, these are the appearance of erosion corrosion. So, we see the appearance that is shown by erosion corrosion effect are basically grooves, gullies, waves, rounded holes, those are the appearances, and as well as we have seen that there could be a directional nature of erosion corrosion on the metal surface. Now, this erosion effect can also be produced not only the solution, even by the gases. Now, let us say a metal surface, on the metal surface, this is my metal surface, and if oxygen gas flows, that time there could be oxide layer formation, thin oxide layer formation, but due to this high velocity gas, and if the oxide layer is not that adherent to the surface, locally some of the oxide layer could get damaged, until it forms another oxide layer. So, it will form further oxidation. So, there would be a dip in the system. So, like that the entire section could get damaged, and the fresh metal surface is exposed to hot oxygen gas, hot gases. It could be CO2 mixture, CO2 plus O2 mixture, so or CO gas. So, that gas can damage the surface by erosion effect. Now, it can also be formed by liquid metal. If a chamber is holding a liquid metal, that metal due to the relative movement of the metal surface could get damaged, and that is a part of erosion corrosion also. Now, as we have said that solid particle which are in the solution, moving solution, those solid particle can be detrimental towards the erosion, and that can lead to erosion corrosion. So, solid particle can erode the metal surface, and there could be erosion effect, and the solid particle, if it is a passivating metal, that case this solid particle can damage the passive layer, and before the passive layer forms, very high degree of corrosion can be possible. And if we have a moving gas, hot gas, that could also lead to erosion corrosion. Now, systems which are under erosion corrosion effect, what are the systems which are under erosion corrosion effect? One is piping system. Then we have, in case of piping system, there are few sections which are much more susceptible to erosion corrosion. For example, bends. Then we have elbows. Then we have particular bends and elbows and sharp turning, or let us say one big pipe is coming and there is a, let us say this pipe, the large dimension pipe, the fluid is flowing, and from that you have a outlet which is small dimension, and this part is more susceptible to erosion corrosion. Why? And this also this is also under the effect of turbulence. And what happens? Now, this section we have laminar flow, and suddenly when it enters into a smaller cross section area, this part there will be a turbulence formation, there will be a lot of turbulence, and before the solution assumes laminar flow. So, this part is laminar flow. So, that means, after entering into the shorter dimension or shorter cross section pipe, the fluid assumes laminar flow after a short distance, but till that point this section there will be a lot of turbulence, and due to that effect the corrosion would be more in this section. So, this is another effect, another system or situation where we can experience erosion corrosion. Then we have pumps, then we have propellers, then we have impellers. So, these are the systems where we can have lot of erosion corrosion effect. Even we can have nozzle duct, then orifice. So, those cases, even turbine blades, there we can experience erosion corrosion effect. So, these are the systems or situations where we can experience erosion corrosion effect. And before I come to different factors which will affect erosion corrosion effect, let me mention that let us say we have a very good laboratory data for a particular metal or alloy system which shows very good corrosion resistance, but it may not be true that that system will show very good corrosion resistance in moving system, or whenever you have a relative movement of the solution or the liquid that it handles, then the corrosion rate would be entirely different, because in the laboratory we have almost all the tests are done in static condition mostly, and even if we have some sort of movement, that would be a very, very small movement. So, it will not actually depict the actual scenario. So, the laboratory test data cannot be considered for judging the erosion corrosion resistance of a particular metals and alloys. Now, let us get into different factors that will guide erosion corrosion. One is definitely the surface film. Nature of surface film, how strong it is, how adherent it is to the metal surface, that would decide the erosion corrosion resistance of that particular metals and alloys. Now, in case of surface film, one more criteria, of course, the strength, adherence, then you have let us say the surface film is very compact and very less of defect, that surface film would definitely act better in order to have, and it would have very good resistance against erosion corrosion. And there are two other criteria. One criteria is the rate of passivity, attainment. This means the how quickly the passivity is attained again. Let us say a metal surface, this is my passive layer, this is my passive layer. If some section is broken, now that case, if this section is broken, that case how quickly the metal surface, the broken layer, the metal which is exposed to the solution, that will form the passive layer. How quickly it will form? The quickness of attaining passivity would decide the erosion corrosion property of that particular, erosion corrosion resistance of that particular metals and alloys. So, the quickness of attainment of passivity, and of course, its strength to resist wear effect, and of course, the continuous nature of the passive film, those will decide the erosion corrosion resistance of a particular metals and alloy, or of a particular metal or an alloy. Now, second effect is velocity. Now, while we consider velocity, we must realize that the velocity would be a factor whenever there is enhancement in the corrosion rate. That is basically the, in the definition we have seen, the erosion corrosion says that there should be enhancement in corrosion rate, and if there is decrease in corrosion rate, that should not be considered as erosion corrosion. Now, when we consider velocity, we generally experience a critical velocity for a particular metal when it is exposed to a particular medium. A critical velocity before that the corrosion rate would be very sluggish, but once the critical velocity is reached, then the corrosion rate would enhance quickly. So, why that happens? Generally, it is related to a breaking down of the passive film or dissolution of passive film, that would lead to enhancement in corrosion rate. So, the critical velocity is an important issue. So, we can decide for a particular metal or alloy system what could be the critical velocity when it is exposed to a particular corrosive medium. Now, then this velocity, that means this is the characteristics of velocity effect. Critical velocity is to be attained before we experience exaggerated effect of erosion corrosion. Then second issue is, it always increases the corrosion rate. Why? There are two ways. One is let us say oxygen, dissolved oxygen is there, or dissolved CO2 is there in the solution, and if let us say a particular section oxygen is depleted, because of velocity, the oxygen, depleted oxygen part will be recovered because of movement issue, because of the solution movement, and the oxygen concentration would be same throughout. And then it increases the diffusion or transfer of ions. Let us say I have a particular metal surface where passive layer is forming. Now, that passive layer always you need, if it is a stagnant solution at that particular temperature, until unless metal dissolution is of course taking place. But at that temperature, if it is stagnant, then the metal ion concentration, once it reaches some critical value, because of the solubility effect of that passive layer, the metal ion will form a passive film and the passive film will grow up. But if somehow I drive away all those metal ions that are forming on this metal surface and which are in equilibrium with the metal and the solution, with the passive layer and the solution, and if we can break the equilibrium, so more and more metal ion should come in order to maintain that solubility. Now, once this happens, though, that time this passive layer thickness goes down. Passive layer thickness gradually goes down, and then you have more and more metal dissolution. So, this is second effect, that is basically because of this we have enhanced corrosion rate due to velocity, increase in velocity, but velocity sometimes decreases the corrosion rate. For example, if we have inhibitor which is added in the solution, now that inhibitor can go to the section where the enhanced attack is forming, enhanced attack is going on. So, that inhibitor, because of this flow of the solution, inhibitor can go there and stop the corrosion effect. So, this is the effect of inhibitor. So, inhibitor can reduce the corrosion rate, and that is happening because of the velocity, and that moving liquid will transport that inhibitor to the section where we have more corrosion, and that inhibitor will try to control the corrosion rate. Now, this is basically the velocity effect. Now, there are some case studies, and these case studies involve the surface film as well as velocity. Now, for example, if we consider lead pipe, and if we consider lead, now that lead pipe can handle H2SO4, dilute H2SO4 for a long duration, and that time we have lead oxide or lead sulphate. Those films form on the lead surface when it is exposed to dilute H2SO4, and it gives very good protection. It gives very good protection because of this passive layer formation, and it can be operational for 20 years. Now, if the solution strength increased and it goes to low to high strength, this is case study 1, and if it goes to low to high strength, lead sulphate dissolves, and once lead sulphate dissolves, now you have less of protectivity of that passive film over the lead surface. So, lead dissolution increases to a great extent. So, that means it is not only velocity, at the same time strength of the solution would decide whether the passive film would be active or not. Active means whether it would be active to give protection against this erosion corrosion.